So now we can just recap what each of these Maxwell equations actually means. So the first Maxwell equation states that electric charges create electric fields. If you have really any complex understanding of how this actually works, this would actually make really good sense to you, and it's really satisfying at the end. But as we stated previously, the first Maxwell equation in integral form is the closed area integral of E dot dA equals the q of the other particle over epsilon. So in differential form, we can go ahead and write that as the divergence of E equals P over epsilon, which ends up working out really, really nicely. Basically saying that if you did end up looking down here at the CIT and the VIT, you define sinks and curls, the sinks and sources along with no flow. The first Maxwell equation basically just states that electric charges create the field in itself, therefore that they create these sinks and sources of electromagnetic fields in itself, which create electric fields. So it's basically just applying to electric fields, saying that electric charges, create electric fields being defined by sources, flows, or basically no flows, and sinks. So the second Maxwell equation says monopoles cannot generate magnetic fields. This one took me a while to get an actual intuitive understanding of, but we see that the second Maxwell equation is the divergence of the magnetic field B is equal to 0. Like I said, through the DIT and the CIT explained, it works out really, really well. But basically saying that no singular charge, whether that be negative or positive or north or south, however you want to put it, can express a magnetic field by itself, as we see the divergence of this magnetic field, of the singular magnetic field without a dipole charge, is going to equal 0 with no magnetic fields. Like I said, the CIT and DIT really, really satisfied these equations. The third Maxwell equation states, or not states, but it really shows, really satisfying, that changing magnetic fields creates a rotating electric field. Basically saying, like we stated up there, that the change of the magnetic flux over the change in time equals this electric field that we were talking about, or actually a rotating electric field, which is defined by the CIT. Like I said, really satisfies it. Basically, just as simple as we can put it, changing magnetic field. So if the magnetic field is constant, or it's not changing, then there's not a rotating electric field. But if this magnetic field is changing in respect to time, then it creates a really nice, satisfying electric field throughout the CIT. The fourth Maxwell equation states that electric currents and actually I have it written better here. Electric currents and changing electrical fields generate rotating magnetic fields. So electric currents and changing electric fields generate rotating magnetic fields. So basically saying J, which is the electric current expressed with area, like previously mentioned. So as J changes, so electric current, so as J, so if we put the surface that we're talking about the system here, and we put J here, in conjugation with the change of E right here, produces this rotating magnetic field about dA, about dA being the surface that we're talking about. And like I said, dA is enclosed by dl, which all makes up dV. So these all satisfy really, really nicely.